Hello everyone, welcome to part 2 of lecture 19. So we were discussing about the glaciers in this lecture. So we will continue that. So in the previous part I talked about the Randolph Glacier inventory. So this is just to continue that one. So if you are interested to work on the snow and glacier related project, then you are supposed to use this Randolph Glacier inventory for identifying the glacier boundary, and then you can further go ahead. Now we will see the tidewater glacier. So these flow and terminate in the ocean. They often break off, that is calve, to form icebergs, right? And here this particular glacier is in Greenland. Ice sheet is said to move at 12,600 meter per year. So you can see that how a glacier can take the velocity. So some of the glaciers are moving at a very fast rate, some of them are very slow, right? So the key characteristics of these tidewater glaciers are calving, marine termination, cyclic advance and retreat, floating ice extension, and their dynamic behavior, right? So this is one of the example of tidewater glaciers, right? And here you can see there is one more image, right. So here it is showing the crevassing a calving iceberg, and this is one image which is beautifully showing how these icebergs are basically floating, right. So we will see the iceberg in detail. The term literally means the ice mountains. The icebergs are huge chunks of floating ice that have broken off from an ice sheet or alpine glacier. These can be high as 5 meter in height, right. Smaller icebergs are known as growlers and bergy bits, right. Since these are hard to detect, they are extremely dangerous for ships. These are mostly seen in Antarctica and the North Atlantic Ocean. Here you can see it is captured by National Snow and Ice Data Center, shows an amazing glowing iceberg located off the coast of Iceland. So the ice sheet is a mass of glacier ice on the land surface that can extend to more than 50,000 kilometers square. Antarctica is witnessing the loss of ice mass at an average rate of 136 billion tons annually, while Greenland is losing about 267 billion tons every year. This is from NASA. The image shows the West Antarctica ice sheets being drained into the sea through the S-shaped glaciers, right. So here you can see the presence of crevasses at the glacier's top indicates the flow of ice over steep terrain, because as I said, it will take the path through the slope, and because of the gravity it will start moving. If the temperature is changed, it will start flowing at the faster rate. Ice caps, these are miniature ice sheets cover less than 50 kilometer square. They comprise several merged glaciers, right. They have dome like shape. Due to their small size, the ice flow direction as well as its surface shape are more influenced by the underlying landscape. This is one image which is captured by MODIS. It is showing the island ice caps, and here you can see this is captured by MODIS, right. The glacier geomorphology is very important. So if you see, the glacier morphology is influenced by climate and topography. Based on the combined factor, they can be of two types. The first one is the constrained glacier and the other one is the unconstrained glacier. So in constrained glacier, morphology and flow patterns are dependent on underlying topography, and resultant of that we have Piedmont Glacier, then we have Cirque Glacier, ice fields, Niche Glacier, Valley Glacier and transaction glaciers. In unconstrained glacier, we have morphology and flow pattern which are independent of underlying topography. So, here we have ice sheets, ice caps and ice streams. These are not controlled by the topography. So, let us see the details of Piedmont Glacier. So, these glaciers occur when the valley glacier spread like a lobe, and here you can see the Alaskan Glacier, that is one of the example. Malaspina Glacier, which is the largest Piedmont glacier, is shown in the MODIS satellite image here, you can see. Then we have Cirque Glacier. So, these are bowl like depression are a result of glacier erosion and are found at the sides of the mountain. So, you can see this kind of depression will make the Cirque Glacier. This is one example. Then we have ice field. So, these are extensive ice areas that are an interconnected series of glacier and ice caps. The image shows the ice field of North Patagonian located in southern part of the South America. It shows numerous radiating valley glaciers here, right. Then we have Nice Glacier. These forms are where the accumulation of ice takes place in mountain side niche like a depression or rock bench and are smaller in size compared to the cirque, right. The image shows a typical example of Nice Glacier. So, here then we have Valley Glacier. These originates from the mountain glacier. These flows down beyond the snow line. So, if suppose if this is one mountain and this is our snow line, above that there will be accumulation of or there will be a solid precipitation. So, this is the accumulation area, but these valley glacier flows down this snow line. This is another example of valley glacier. So, this is from Sentinel-2 data. It is showing the large valley glacier found in Alaska, right. So, here you can see how these are coming. Then we have transaction glaciers. These are radiating interconnecting glaciers that forms when the bedrock valleys are deeply dissected, that's resulting in the overflow of ice to the cols located between adjacent valleys, right. So, here you can see. So, the image shows a typical transaction glacier here. Then we have arete. Aretes are thin jagged ridges that are formed by glaciers erosion between two bowl shaped hollow. So, here you can see this is one, this is the second one, and here we are calling it arete, right. And this is where we have the snow accumulation, and we will also have the lateral moraines here in both the sides. Then we have fjord glaciers. So, the glacier erosion feature that forms between the steep slopes and is represented as a long, narrow and deep sea inlet, right. Then we have Ross Montagny. These are asymmetric bedrock hills which has a gently sloping Stoss side and a quarried or plucked lee side. Here the image is showing the Ross Mountain, and here you can see the Stoss, and this is the lee, and this is the ice flow. Then we have trim lines. So, you can see these white marks arrow. So, these erosional features mark the maximum vertical extent of the previous glaciation, right. So, here you can see. So, these are clearly visible here. So, the image depicts the valley side trim lines that mark the former thickness of the glacier, right. Then we have hummocky moraine. This is another important aspect. So, the hummocky moraine forms when there is a landform melts out beneath a cover of debris that float to the current position. The image shows the formation of hummocky moraine. Here you can see this is the first one, the surge, this is post surge, and this is the landform melt out. And here after the melt out you have the hummocky moraines, right. Now in glaciers, particularly at the snout of the glacier, you will always see moraines, right. So these are ridges of debris that are laid down by a glacier or pushed by it. So you can see these are the examples of moraines. So the image shows moraine formed at the lateral margin of the glacier. This is the schematic figure on the right, shows the types of moraine. So here you can see this is lateral moraine, this is medial moraine, this is again lateral moraine, recessional moraine, terminal moraine. So these are very clear from these examples. When we talk about the terminal moraine, so these are the moraine ridge making a maximum limit of the advance of the glacier. They form at the glacier terminus. So here you can see the terminal moraine, and the image depicts the terminal moraine of the former ice sheet, right. Then we have medial moraine. So these are the debris ridges that form at the surface of the glacier and run parallels to the ice flow direction, right. So here you can see this is the medial moraine, and this is running parallel to the ice movement. Then recessional moraine, it is found behind the terminal moraine, right. So here you can see these are marked here. This forms during the temporary halts or advances of glacier retreat. Then we have proglacial lakes. The proglacial lakes originates at the glacier's margin as the accumulation of the meltwater takes place against the hillside as well as the glacier debris ridges. These are found within the quaternary deglaciation records. The figure shows the influence of ice advance and retreat in evolution of the proglacial lake. The figure A and B indicates the longitudinal view, while C and D shows the plan view, right. So these two are the plan views. Now we have proglacial lakes. So you can see different types of proglacial lakes from different parts of the world. Now we have supraglacial lake. The supraglacial lake originates when the accumulation of meltwater takes place in topographic depression or glacier top, ice shelves as well as ice sheets. These are the lakes that are found on the surface of the glaciers. So you can see here the whole thing is glacier here, right, and here on top of that you are having a lake which is called supraglacial lake. It is the most common type of the ice damped lakes. These are some of the examples. So how exactly we are looking at these glacier and glacial lakes? So remote sensing is one of the tool which can be effectively used in such studies. So you can see the Siachen glacier, right, and if you see this is the location and this is the satellite image. This is also a satellite image, but this is the zoomed view. So how it appears in your satellite image. Then we have Jemu glacier. So this is the Jemu glacier, and you see this is the zoomed part of the Jemu glacier. So how they appear in your satellite image when you have them from different space agencies. So we have two major sections. One is space-borne remote sensing data, another one is airborne remote sensing. In space-borne you have optical and thermal sensors and the radar. So in airborne you have mainly radar and lidar, and these two different sections of the remote sensing are widely used in snow glacier studies, particularly in cryospheric related hazards. So these are some of the data sets which are available, and people have used them very effectively in cryospheric related hazards or studies. So we have already discussed in several lectures what is the advantage, what are the different advantages of remote sensing in natural hazard studies, and particularly when we talk about the cryosphere, the field investigation is very tough. going to that collecting in situ data in different high altitude regions is very difficult. So that's why these spaceborne data set and airborne data sets are the prime inputs that we are using in our research. So here you can see that in this particular work different methods have been used to identify the snow cover or snow on glacier present on a particular area. Based on these inputs you can analyze how they are changing over the time. So with this I will end this lecture here. These are some of the references that have been used in this lecture, and we will continue this cryospheric module in the next lecture. Thank you.